number 5, the product rule. So we've been developing derivatives and keep adding more and more information so that we can take the derivative in different situations. Eventually, you'd like to be able to take the derivative in any situation, so you'd have a way to do that that didn't take so long. So we started off with the longest way, right? We had our definition of the derivative, and we plugged things in. And then we discovered shortcuts, which made our life a lot easier. But we still have some areas that we can't do the derivative of. So we've learned that if you add two derivatives, add two functions together, that you can take the derivative of each one separately. So the idea is, well, what happens if you multiply two functions? Maybe it would work if you could just multiply the derivatives together. And that was the same thing that Leibniz guessed. He says, well, if when we add them we can just do the derivatives separately, why don't we try it with multiplying? Now we have a little example here to test it. Let's say you have x and you have x to the 4. Multiplying those two functions together is easy because x times x to the 4 is just x to the 5. And the derivative of x to the 5 is easy because that's the form that we've done most of our derivatives. Just bring that 5 in front and subtract 1 from the exponent. So the power rule says that that derivative is 5x to the 4. So it's a good example to test. Can we just do the derivative of each one separate and then multiply? Well, if we do the derivative of just x, we get 1. And if we do the derivative of just g of x, we get 4x cubed. And then if we multiply those two derivatives together, we still get 4x cubed, which isn't the same as what it should be, which is 5x to the 4. So our initial guess, and this is how mathematics sometimes works, is you make a hypothesis to say, does that work? And then find out that it doesn't. Then you go back to the drawing board and try to figure out what are the patterns that I see when I'm working on these to figure it out. Now, working through this, the pattern was actually quite a bit more complex than just multiplying two derivatives together. How's that for a formula? Does it remind you of like sum and difference identities, where you have like 4 things all multiplied together? So what it says, and these are just two different notations of the same thing. I believe the Leibniz notation is on your formula sheet. What it says is you keep one of them the same and multiply by the derivative of the other one. Then keep the other one the same and multiply by the derivative of the first one. And that's what we have listed here at the bottom. You just keep the first one the same as it is and multiply it by the derivative of the second one. And then you keep the second one the same and multiply it by the derivative of the first one. And the order doesn't matter. So you can simplify this even easier by just saying keep one the same and multiply it by the derivative of the other one, then switch it around and add those two together. So what does this look like? I can go back, yep. I know, I'm getting excited. So what does this look like with an example? Well, for this, x squared times 2x minus 1, when we're finding the derivative, and you can do it directly just like this, the derivative is going to be, notice I'm going to do some highlighting here just so that you can see some things. Here is my first function multiplied by my second function. So one of the things with the product rule is you have to be able to recognize where is one function multiplied by another function. And does it make sense that our multiplication sign between two things would be right there? Then when we go to do our derivative, we've got our first function, nothing changes to it. and we multiply by the derivative of the second one. Does it make sense that 2 is the derivative of the green one? Then we keep our second one the same. And then we multiply by the derivative of the first one. Does it make sense that 2x is the derivative of the first one? And you are going to be able to go directly from that question to that answer as you practice these, because you'll just get used to, okay, keep one the same, derivative of the other one, plus keep the other one the same, derivative of the first one. You can, if you like, to separate and use Leibniz notation. If you want to use your formula sheet more fully, you could say, well, I'm going to make x squared my first function, so then the derivative is 2x. I'm going to make 2x minus 1 my second function, so the derivative is 2. And then you can use the formula, because all the formula says is dy dx is equal to u dv dx plus v du dx. And then you just have to replace each of these four things with the things you've put in your list. But you're going to find that you're going to be able to do it directly. And it's easy to do, and it's just a matter of going one step. And often with derivative questions, they're not even going to ask you to simplify. So you're going to be able to answer this question in one step just like that and be done. Now, if you wanted to simplify, I mean, we could multiply this out, combine our like terms, and we could get 6x squared minus 2x. If we think about this question, I did ask this question or one very similar to it earlier, before I taught you the product rule. And I said, we don't know how to do the product rule yet. How could we work with this one to change it into a form that we did know how to do? And so, does it make sense that I could distribute that x squared? And then I would get 2x cubed, minus x squared. And this is in a form that we've learned how to do before. So this one's really easy. And if I did the derivative of this one, bring the 3 in front, this will give me 6x squared. Bring the 2 in front, minus 2x. Notice we get the exact same answer. In fact, with this one, when I compare the work, if I wanted a simplified version, it looks like it would have been easier to multiply it out to begin with and then do the derivative rather than using the product rule. But we're going to get some that it doesn't make sense to multiply them out, or they're going to be too big or just too awkward to work with, in which case the product rule is going to be a lot nicer. So we'll do another couple together. Here's another notation for you. If you have a question that says find d dx of, this in front of something means take the derivative of that. So using our product rule, again, I'll get out my highlighters. Does it make sense that this is one? Oh, I liked using yellow first. This is a first function. The multiplication is right here. And that's green. There's my second function. Can you see where the multiplication happens? Okay. And that's going to be a big thing in a lot of our derivatives, is just recognizing the form that it's in. So if we can recognize that this is multiplication, again, I'm going to want you to go directly to this, and this should have dy dx. So our derivative, again, we've kept the first one I'm having such color problems. There we go. Kept the first one the same. Then we have the derivative of the second one. So does that 10x, you recognize that the derivative of 1 plus 5x squared. And then we keep the 1 plus 5x squared the same. And then the 3x squared, is that the derivative of the yellow one? Yes. So again, if you wanted to, you could have all of these things off to the side for yourself. Eventually, you're going to find you're going to become good mathematicians that are somewhat lazy, and you don't want to write that down because you want to do it faster. And then if you multiplied it out and simplified, that's what you would get. Again, looking at the format of this question, it might have been one that I decided to distribute right at the beginning, because it's not hard to distribute an x cubed into that. And then I probably would have got the final answer simplified quicker. But it's also nice to see that using our old techniques and using our new techniques give us the same answer. So both example 1 and example 2 were ones where you might say to yourself, yeah, maybe I would like to multiply this out first because it would be easier. It all depends on, do they want my final answer simplified or not? If they don't want it simplified, then maybe using the product rule right from the beginning would be helpful. So here's one where I would say it's about equal. Equal to multiply it out or to use the product rule. Because again, you see that multiplying this one out is a little bit more complicated. You're going to have to distribute the first ones, the outside ones, the inside ones, and the last ones. Again, we'll color code. Here's our first function multiplied by our second function. We keep our first function the same. Then what's the derivative of the green one? It would be 6x minus 1. Keep our second function the same. What's the derivative of our first one? It's just 6x squared. And if you want to simplify it out, you can. This one I'm going to leave unsimplified. If you want to simplify it on your own, you can. If you want to, I can click the boxes off so you can check later if you were right, but I think you'll be fine. Everybody good? So if you want to check these later, there they are. You can pause the video. I'm not going to let you write that down, though. How's that? Okay. Whew. All right. So I just show you that one. You want to see those other ones later. I'm pretty sure you can multiply them out. But I don't want to waste our time doing stuff we already know how to do. Okay? So I want you to try example 4. Example 4 are ones where the product rule is much better than multiplying out, because we start adding functions like tan and natural log of x and e to the x in there. So here's your first one, and I'll put up the answers after you've done them. There's the first one. How did you do? Did you remember that the derivative of natural log was 1 over x, or did you have to flip back and look it up? Flip back, okay. Might be. I would say you're going to memorize them all because it's going to save you time. You don't want to be flipping to your formula booklet all the time. All right, quick check on this one. And of course, if you wrote the tan x times 4x first, plus 2x squared minus 1 times secant squared second, that's fine. So you don't have to remember which one you have to keep same. You can, the order doesn't matter. And have you got the last one already? Yes or no? No? Okay, I'll wait a bit. All right. So again, it ends up taking a lot of space And it wasn't that hard, but it looks complicated. It looks sophisticated. Well, this is the slope of every single tangent line to that graph. Whatever the graph of sine x plus cos x times e to the x plus 1 would be, this is... Why would you do such a thing? Because we can. Right? And we look sophisticated in the process. Okay, right now, this unit, we are developing the skills of working with derivatives. You ask the question why, you might be, scared that you asked that because our next unit is applications of derivatives. So that's the why. And that's when things get complicated. So you might regret asking the why, but... Oh, simplify, I know. So again, we have to be reminded that when we find the derivative, that derivative finds the equation of the slope of any tangent no matter where we are on that graph. So if we had the graph of 2x times sine x, the derivative you could find with the product rule, and that equation is your gradient function. That tells us the slope of any tangent line anywhere. So if you wanted to find a specific one, find the gradient of the, it should be tangent, I think would be a better word here. Find the gradient of the tangent of g at x equals pi. Now you can just plug in pi for x. Okay? Now cos of pi and sine of pi are on your unit circle. If you think about the coordinate, remember that the x coordinate is cos and the y coordinate is sine. So what's cos of pi going to be? -1, and sine of pi? 0. And the math and the simplification isn't too bad. So we can do questions like this, where we find the slope of the tangent, or like this next one, where we find the slope of the normal. So I'll give you a head start. So there's our derivative. Remember that derivative of cos is negative sine, and you think of the cos graph, your tangent lines will go down to begin with, which might help you remember that that's a negative sine of x. Now, when working with this, you could factor out that e to the x that's in common. Maybe that makes life a little bit easier, but in this case, it wouldn't make a difference if you didn't factor it out, but you could factor it out. Then when you plug in pi, sine of pi is 0, cos of pi is -1. And so when we multiply that through, our value at pi is -e to the pi. That'll be the slope of your tangent. So what are the normal slope going to be? It's going to be the reciprocal and the negative reciprocal. So it becomes +1 over e to the pi. You wouldn't have to. It will work out fine if you didn't. But you'll find out that, especially in some of our later questions, you will get on your exam questions that say, show that. And in those ones, it's sort of like a little mini proof. You have to find the derivative and show that it equals this. And often you have to factor in those ones to make it look like the way that they want you to. So it's good skill to see and to work with. And also, some of them will be able to simplify once we factor. Now, I was going to give you one question where it was 3 things multiplied together just to see what that would look like. So let's pick 3 functions that are quite different. Let's choose x to the 7 multiplied by sine x multiplied by the natural log of x. Okay? Now, when you have 3 things multiplied together, what happens is you will have a product rule inside of a product rule. And it will look like this. So first of all, I'm going to say my main multiplication is here. I'll make that a bigger dot. How's that for woo? And then color coding things like I did before. This is my first function multiplied, and this is my second function. I'm going to slide that green up just a little bit to say within my second function, I have another smaller multiplication happening in that one. And I have a first function in here and a second function in there. Are we ready? So the product rule says keep the first one the same. Okay, that's easy. Let's start way over here because this could be a long one. Keep the first function the same. That's easy. That's my x to the 7. Multiply that by the derivative of the second function. Well, my second function is the green one. What's the derivative of the green one? It's a product rule. So how do I do that product rule? Well, I keep the first one the same, derivative of the second one, plus keep the second one the same, derivative of the first one. Good. Does that make sense? Plus, I'm still working on my initial product rule. Now I would keep the second one the same, sine x times natural log of x times the derivative of my first one. So when I color code this as my answer, can you see that we have kept our, whoa, wrong color. We've kept our first one the same, right? And then we kept our second one the same. And after keeping the first one the same, we did the derivative of the second one. But the second one had a product rule inside of it. So how do I do the derivative of the green? Well, keep one the same, derivative of the second, plus keep the second the same, derivative of the first. And then we've got our second one stays the same, multiplied by the derivative of the first one. So we could do 4 or 5 of them. Just keep going bigger and bigger and bigger. And they get long, right? I almost ran out of Smartboard.